Alrighty, good morning. Welcome. Thanks for coming out. I know it's always a little difficult in the last day, like in the early morning session. Everybody's kind of conferenced out by now, so thanks for coming. My name is Mark McLean. I am a member of the software team at Arista Networks. I was a former Neutron PTL back in the day, a long time ago before Miguel. So, been doing Neutron for a while. Probably responsible for some of the things for operators. You'll probably curse at times and wonder why that happened. I apologize in advance. So what I'm going to talk about today is kind of routing in Neutron. It's a little bit of a survey to kind of give you an idea, an overview of the different options, a little different trade-offs, and just kind of give a view of the landscape. Over the last couple of years, routing has evolved from something that was nothing more than testing, a vehicle for testing in the infrastructure, to something that's deployed in production. Early on, in the early years, we kind of found out the hard way that people were deploying some of these agents into production at massive scale, and the agents were really never designed to do that. So we're going to kind of dive in a little bit to just kind of the underpinnings, how they work, different choices. If I didn't talk about Neutron just with the kind of the overview of, kind of the reference, Neutron is just a fleet of microservices from L2 agents, L3 agents, DHCP. This is kind of the reference architecture. If you're running particular plugins, this architecture is going to vary, sometimes a little, somewhat significantly. A lot of times, the names may change, but the functional elements, when you look at the different solutions, are approximately the same. And so kind of talking about some of the deployment scenarios, with the reference architecture, you're going to have, you got your mix of, you could have flat, you could be running VLAN networks, you could be running overlays with, say, VXLAN, or another encapsulation format. You've got, the Neutron server itself is not part of the data path, and you have a network node, and you can have, more than one. You could have, some fleet of them. It doesn't really change whether or not you're, even if you say you're running hierarchical port binding or one of the other options available, you could have VLANs within the rack, VXLAN across the L3 fabric. There was a session on this yesterday a little bit where they talked and touched on, actually, no, sorry, I skipped ahead. One of the other options is if you take a look at some of the solutions, they'll do basically, it's like host-based routing, where it's all overlays everywhere, but the hosts themselves are actually routing the tunnels. So it's completely L3 fabric. The L2 tenant networks are effectively, via replication. You have all the different issues of, how do you deal with broadcast traffic, how do you deal with multicast, and the unknown unicast. For some deployers, this gets to be a touchy subject because you have, it kind of melds a little bit about, where's the delineation between the team responsible for networking, where's the team responsible for compute. So, in this scenario, you can scale very well, but you also have some trade-offs in the different solutions. What's interesting about this one is that you really, if you start taking a look at the survey between the different vendors and what they support, it becomes a wide variety of, how is this managed? There's not kind of necessarily a standard way for doing it. And then what I touched on a moment ago, or what I meant to start on a moment ago, which is routed networks. They had a session about this yesterday. The video, you can find it. I think it's already posted online. What's interesting about routed networks is that in the case where you don't necessarily care about overlay tenant. You don't care about necessarily isolation. You can have a set of provider networks. You get very efficient data path because you don't have to deal with NCAP or DCAP. Primarily you just want a workload to end up on an endpoint. You assign, pretty much the IP address is, late bound. It does have some issues in terms of, how can you migrate, because if you're bound to a particular segment, you can't really migrate outside of that segment. You can go to another host, but if you go to another rack, your IP address is going to change and you're going to break the world. So, applications can be designed around that, but that's one of the things to consider. In this situation, you have your fabric at the top. Each of the racks is basically assigned a subnet. Typically, you're not necessarily going to need floating. You may not need floating IPs in this situation. A lot of times when you find deployers who are running this, they're basically just assigning a predefined prefix for the OpenStack compute and then routing it throughout the data center. If you take a look at, because question comes up frequently, like what do you do with, kind of ironic, really the story doesn't change too much except for versus having networking managed on a compute node or having an agent or some service running compute node managing the networking, you have to push it up into the top of rack. It's somewhat interesting because there's some rudimentary stuff built into Ironic, which is not necessarily designed for production usage. And then so when you start taking a look at the various vendor options that are supported at top of rack, they diverge differently. They have different supports. So you really have to pay attention to details about what's supported. And so level setting with that, if we really take a look, what is Neutron Layer 3, originally the service was kind of birthed for testing. We co-located all the services, on what was called the network node. We're running with Linux network namespaces, and they were basically very simple static routing configured with IP tables. If we needed to run metadata services, we'd spawn a metadata server within that namespace. And so if we take a look of kind of like that, just kind of give a real basic kind of underpinnings of what's going on. So I've got just a basic router running. So we see, Q router namespace. Let me make this a little bit bigger. Now, the Q is kind of a historical artifact that has never gone away. When we renamed the software from Quantum to Neutron, for operational use, we couldn't break running users, but even now, how many years later since we renamed it, we still can't break operational users. And so there's really no migration of namespaces. So if you ever wonder where the Q prefix comes from, that's why it exists. So if we were to dive into the namespace, you're just going to find different interfaces. For comparison, just to kind of give you an idea, if we were to look at the actual router on, oops. So if we look at that, so we kind of have our corresponding, router interfaces. We have our public interfaces. We have, our internal interfaces underneath the hood. Names look similar, familiar. They're basically some kind of, we're basically taking the UID and kind of morphed it from there. And then so we have that. It's very simple. If we were to take a look at, what's running on what's the routing table look like. Very flat, very static. It's like, hey, we have the links we're immediate to. What's interesting is I mentioned metadata services in the Neutron node run on it. So if you were to take a look at what's running here, you see that we have HA proxy. In the Pike release, this is one of the newer changes. So that basically, is newer. So previously, the metadata service was a Python binary that used up a lot of RAM for a little bit of functionality. When basically you just needed a very thin proxy layer, so it was rewritten to run with HA proxy. If we take a look at what's going on with IP tables, it's fairly static. I mean, there's not a whole lot going on here. We have the SNAT for rules, so for any VMs that are behind the firewall and behind the router, we're going to get NATed, and it's pretty simple, pretty straightforward. This is what's written. This was basically been available since Folsom in some form or another. What's interesting about this is that the network nodes themselves, when this was born, this was all for testing. So it's like, hey, we have a very simple node. It's in that Linux network namespace. It's in exactly one place. Hope your cloud never breaks. And then, that's... So it didn't exactly work and go over well over time. So, oops. because primary problem we found is that network nodes started, they could become saturated. You could have so many network namespaces if you're running public cloud, even if you're running a large enterprise cloud, you could have so many network namespaces that the node simply couldn't keep up, became a choke point. And so over time, features were added to improve HA, and we'll kind of touch on those a little bit. So just kind of recap about what's in a network node. It's a very simple Linux network namespace. That's pretty much the only isolation that we use is network namespace. We don't do any other isolation in terms of processes or whatnot. So that processes that run in a namespace still see the entire file system. So it's just very simple isolation. It manages the floating IPs. So if we were to go back to our example and just to kind of show you. Okay, and see if you look at the last line right there, you'll see where the .4.11 destination NAT was mapped in for floating IPs, and so that's conceptually, that's the namespaces. They're pretty simple from that point, just to kind of give you an idea of what we're doing. And so, it manages NAT, manages source NAT. We talked about, what's going on. So, but when you actually take a look at the data path in terms of legacy, let's say you have a workload that's spun up on a hypervisor. If it's going north and south, if it's exiting your deployment, it's got to hit the top of rack, go across your fabric if it's in an overlay, hit a network node, be processed, and then eventually exit into, the data center infrastructure. Not necessarily efficient, but conceptually, operationally, fairly easy to work with. So, one of the things when we start talking about the different routing infrastructures is like, what kind of complexity do you want when you're doing operations? My background for a long time was in operations, and so, in running clouds is, what employees do you have available? How big? What does efficiency or their operational ease? What trade-offs do you want to make? There's really no right answer that's universally applied. You have to take a look at each unique case. And where it gets more interesting, if we start taking a look at this, let's say we have a tenant has two networks. They have a VM that's on the blue network and a VM that's on the orange network. And because of the way the legacy works, if the VMs wish to talk to each other, even if they're located within the same rack, the packet has to traverse the network node. So you end up with like the really almost like spaghetti routing. Certainly not efficient. Certainly, it becomes a choke point, especially if you have a workload that has very heavy east-west traffic. So you've got some of the efficiencies, but they're also, simplicity is nice, but simplicity comes at a cost. Data path can be very inefficient. You can have congestion. You can have choke points. Other interesting thing is that we're not sharing fates here. So if your network node goes down, you can't talk. If you lose your hypervisor, even though the two hypervisors have east-west traffic in the same rack, you're no longer able to communicate. So that's one of the challenges with the legacy. And so, we'll kind of touch on ways to mitigate that in a bit. So with HA, one of the first approaches we came to with the Neutron team is like, hey, let's just create more namespaces. So effectively what we're doing, spin up, multiple nodes. We're going to copy that namespace. We're going to copy the construct. We're going to use keep alive to basically shuttle the state and ensure that either, one namespace is active and the other one's, passive, basically prepared and ready to go, and keep alive just bounces back and forth which one's active and passive. Gives you HA, still not necessarily fate sharing. You can still have points of congestion, can still have some issues there. Does add a bit of complexity to the operation because you're not always sure, whereas in the original case you can go in and be like, hey, for a small deployment, I know exactly where my router namespace, I know exactly which one's active. When you get to the legacy case, you don't necessarily know what's active. but it solves an issue. It works for, and you know, if you're doing large scale, it's something that you want to have incorporated if you're running with the reference implementation. But added to that was DVR, was kind of the next evolution, where it's basically, let's spread out routing throughout the cluster. Let's spin up little mini namespaces that we put on each of the hosts. Conceptually, the namespaces themselves look exactly like what you would see on a network node with some small tweaks. So now you have a router namespace with every tenant. So in the case where you have a floating IP assigned to a VM, you can get very efficient routing. I mean, you can basically go from the VM, it can exit the host straight out into the fabric and be routed north-south without ever touching a network node. Hyper efficient. You don't have to worry if your network node's up or down. Who cares? You know, it's nice. You know, within operations, we all know things fail, so at least you have your blast radius is a lot smaller. East-west, even nicer. Say they're in if you know the VMs are in 2 adjacent chassis, you know, at worst you're hitting the top of rack switch. Again, pretty close to fate sharing. You can talk with the network nodes up or down. As long as the state's in there, you're good. Now, with DVR, if you're doing public networks and you're doing floating IPs, you know, so one of the considerations is how does your provider network in public, you know, if it's a public or provider network, how is it available? You know, if it's a flat network, it's got to be available on every hypervisor. If it's an overlay network, it's a little bit different, it's easier. If it's a VLAN, the VLAN has to at least be available at that TOR. You know, the networking is going to run on the host. So again, kind of, you know, when it comes to an operational side, you know, does the networking team and the compute team, you know, who's responsible for which delineation, you know, and that gets into this kind of team dynamics. And every organization has a little bit of a different opinion on what's the right way. And I've seen a variety of different solutions that work and work very effectively. So kind of like, you know, so you have DVR, but always since day one, with Neutron, it's always been pluggable. You know, you've had monolithic plugins, you've had ML2 plugins, you know, so one of the other kind of things you have in a difference of reference implementation is kind of like, you know, some controller-based solutions, and kind of one of the ways you can do routing, and this is kind of generic, not necessarily specific to any one, which is, you know, you can basically do it via like OpenFlow rules or flow rules where you can just create virtual L3 elements. You know, you can basically run the entire L3 topology by applying flow rules. You can take a packet, you can look at it, you can decrement the TTL, you can rewrite headers, and then you can determine what the next hop is after applying all the rules. Nice thing about this is that you can basically have multiple points of ingress and egress depending on how the flow rules are propagated across the virtual switches. You know, so, but within that, you have a couple different things you have to look at depending on the solution. Is in some cases, the flow rules can be established well in advance. That can actually add to complexity because you have to account for every case, whether you in advance and handle it. You know, the other alternative is you wait till you see the first packet, figure out what to do, and then cache that result, and then run it and then use that cached result from then on. Nice thing is that you don't have to go the complexity and exponential growth of rules, but the other side of it is your first packet can be kind of slow. So, you know, once it's cached, it's going to move through fast because you're going to read it. And so, you know, some examples, you know, of some of the controller base, you can have like OVN, MidoNet, Daylight, Contrail. So if I take just to kind of give you an example, so here's like a flow list I dumped out of like an OVN system, basically from the router namespace. It kind of gives you an idea where the flow rules are written. Again, it's the same thing that we were looking at before. It's just a different way of achieving it. Same end result. And in general, these principles are applied here, apply to a number of different solutions. So I just picked this one out because it's open source and easy to access if you want to play with it. So, you know, so when you have the flow-based rules, it's still, nice thing about that is you can, you know, the different systems scale differently. Some of them have very good high availability. Some of them have very good scale out. Some of them require intensive resources. So as a deployer, when you go through and you have to start making these choices, you have to kind of evaluate that. How big is the OpenStack cloud? If you're running a smaller cloud, maybe you want one set of choices. How big and what's the expertise of your team? You have to factor that in as well. And then kind of, that next evolution, I think that everybody's been asking for since like the first time we put routing in, this is like, I want BGP, I want dynamic routing, I want this, I want to integrate, I don't want to have to put static routes into my deployment. So with Neutron, you kind of have a BGP speaker. Nice thing is you can, through peering relationships, you can establish a cloud and you can have it announce prefixes. It can basically be any prefix. It doesn't have to necessarily be RFC 1918 space. It can be publicly routable space. Interesting caveat is that it needs to use address scopes, which is to work, and also kind of best applied if you're using subnet allocation pools. So a lot of times when you see some of the workloads and you start, and when I've talked with different people deploying on OpenStack, is people are like, well, I'm really concerned about NAT, but because they have either private address space or they're concerned about how it scales out. But one of the considerations is does your workload actually need private address space? A lot of times within enterprises, you find wide, very large blocks and prefixes available that can be used internally that don't necessarily need NAT. You can protect them, and you can also, via allocation pools, you can make them self-service. Because one of the biggest concerns is everybody's like, well, I got a team, they're going to spin up a network. I don't want to have to go through and manually start allocating, And then you get other enterprises who go through and say, no, I'm going to manually allocate your provider network every time. But with subnet allocation pools, it's kind of nice because you can set rules up. You can say, hey, a team can go through and request, say, a /24, and they can get this many addresses allocated to them. But it can come out of a central bucket. It can come out of a, set of address range, which is viewable by your entire, within your entire organization without having to use NAT. It makes end-to-end connectivity a little easier. It also removes some of the choke points. You can take advantages of east-west routing. And then you can also take advantage of where you get into Neutron's dynamic routing. So, we still have our layer 3 agent. It's running static images. It's running in static, like namespaces, static routing. It still looks the same in this. Kind of what we're adding here in this situation is we're adding a sidecar effectively that is an agent that speaks BGP. It's going to talk into my provider router back in with my infrastructure, and it's basically going to say, hey, the next hop for the 10.9 network is going to be 192.0.2.11, and if I want to talk to 203.113 network, it's going to be 2.22. From an operational standpoint, fairly easy. It's also nice because you can add addresses. You don't have to go through and reconfigure routings for static routes. You don't have to go through and say, hey, I've added more capacity in my OpenStack deployment. I've added more address space. You don't have to reconfigure the network all the time. If we take a look at with floating IP, you can do some interesting things because you can announce the floating IP back in the fabric as well. So let's say at the VM1 at the top, I added in floating IP and bound it in. So now my 192, 2.99, I can announce and say the next hop for it is here. I know some out there are concerned, well, hey, I don't want to announce a whole bunch of /32s into my network, but in some use, it depends on, again, what deployment, what hardware, what architecture you have available, what internal routing protocols you're running. In many cases, this is very easy and it just works. And then kind of, lastly, hardware routing in terms of Neutron is really kind of all over the map in terms of what's available. You have different solutions from different providers. A lot of times what you're going to find is that for hardware routing, you're going to need, it's going to be a very customized solution, not necessarily portable. So, in getting a multi-vendor environment, and when it comes to hardware routing, and Neutron is actually a bit of a challenge still. With some of the discussion around, how do we make L3 flavors, how do we make service providers work right, it is possible to do that. You can do layer 3 plugins and make that work. But from a deployment and challenge standpoint, it does add some complexity. Typically, your team has to understand kind of the intricacies of Neutron routing in terms of just from the API level, not of actually the data path level. But, the benefits are kind of, you're going to get line rate pretty close to it. If you have within your existing network infrastructure, you can use your existing management and monitoring tools. You have visibility. Some of the challenges, if you're running the reference implementation, you may not have the greatest visibility. If you're running some of the controllers, some of the open source controllers have very good visibility, some very good monitoring and management tools. So you have to kind of evaluate those things. Also, when it comes to hardware, hardware is a finite resource. So you can have different limitations depending on the particular silicon that's being used in terms of, VXLAN or VLAN, how many, how does it do overlay routing? Some platforms do overlay routing very well. Some platforms don't do overlay routing so well and have to require second passes or other tricks to make it work. Some platforms have, a wide number of VRFs available on the boxes. Some have very low. So you kind of have to deal with that. And then kind of the last one is like floating IPs. Some of the hardware will do NAT pretty close at line rate. Some hardware will not, the performance in NAT's not good at all. So you kind of have to dive into the data sheet, see what's available within the platform. And if you're doing, say, source NAT, it gets even trickier because how do you manage that? If you're deploying, a lot of times where you see hardware routing in some deployments, it's heavily optimized to the east-west case. But all the north-south, any of the NAT traffic has to go through a network node, so you're back to like what we were originally when we started with the basic, Neutron network node is still in the data path for a wide variety of traffic. And so that's why, I touched on earlier, it's like I recommend considering subnet pools when you take a look at how you're deploying. A lot of times you can kind of skip some of the headaches of NAT and get advantages and also simplify things. So with that, that's kind of the overview of kind of everything, kind of high level, just kind of giving this tour. Are there any questions? Yes.
With the nomenclature of legacy, does that mean that you guys expect legacy will die someday?
So the question is, with the nomenclature of legacy, do we expect that legacy will die someday? Naming things is hard, to be honest with you. And so, it's like, how do you coin a phrase that kind of says, well, this is what we started with. People are deploying it. Is it ideal? No. And so that's kind of where the legacy kind of phrase was coined, which is like, if you're going to go with the reference implementation, you're going to go with what's available in the Neutron tree. It's like, look at DVR, look at HA. That's the future. But do I think legacy is going to die? Probably not. It's like one of the, all things in open source, there's always someone still running it. So I think as we all learn trying to go from Nova Network to Neutron, that process took, way longer and way longer. And there's never a nice mapping. The one benefit I will say in terms of legacy to DVR is, there is code with the Neutron as an administrator. You can move routers between being legacy mode and being into HA and distributed, and you have that ability as an administrator to move it around and kind of control how you do that. I just don't see it going anywhere. Fundamentally, it's also used for testing because it makes things very simple.
Let me put it another way. I chair the F3 subject meeting every week, and we are not discussing.
Yeah. I think there would be a riot if Miguel proposed getting rid of it. So, yeah. Any other questions? Yes.
What role does the network node have when you move away from legacy to DVR?
So the question is what role does the network node have when you move away from legacy to DVR? And so the network node still exists to provide services, say, for metadata. You still have to deal with SNAP traffic for the network node. Those are primarily still the two use cases. With metadata services, you can actually, the DHCP service actually can provide metadata service as well. So in some cases, you can go with DVR and you could almost make the network node almost irrelevant, but pretty close to it. So there's alternatives. I've seen deployments that don't have network nodes for routing, but use network nodes for DHCP. Yep. Any other questions? All right, thank you very much.